So we have come to the last component of the biophysical model. So the four components, as you know, are dendritic processing, action potential generation in the axon hillock, axon propagation, and synaptic transmission. So we have come to the fourth one. So like I was saying, there are many aspects to synaptic transmission or neurotransmission. We'll be focusing only on the postsynaptic side, right, to show how PSP is generated, because we know that in the case of excitatory neurotransmission or excitatory synapse, we have an EPSP, and inhibitory synapse we have an IPSP, right? And this PSP has a graded potential; it can vary, right? So how do you show that electrically? So when a vesicle is released, when a vesicle releases its contents into the synapse, right, that produces a brief increase in the conductance of the synaptic conductances. That is the conductances which participate in the synaptic transmission, and that brief increase can be modeled reasonably well by this function, right? A into t power at into t power minus t by tp. So if that's how conductance changes, how does the voltage on the membrane potential on the postsynaptic side vary? So that can be given by this equation, because this is circuit model, this is a synaptic conductance, then there's a membrane capacitance, and the third branch is the sum of all the other uh, ion channels on the postsynaptic side, right? We are assuming that they're all passive channels, so they're like leakage channels. So we just combine them into one branch. And that equation is given by C dV by dt plus G sin times Vm by E sin. E sin is this voltage, right? Plus Vm minus V rest, right, by R is equal to 0. Basically, it's Kirchhoff's current law. Now, to show that the PSP is basically a deviation from the baseline, from V rest. So to give the answer in terms of that deviation, so we need to look at a quantity which is Vm by V rest. So if you rewrite the equation in terms of this new quantity is small v is equal to Vm by minus V rest, then you have C dV by dt plus G sin times V plus V rest minus E sin plus V by R is equal to 0. So if you move things around, you get C dV by dt is equal to minus of G sin plus 1 by R times V plus G sin times E sin minus V rest. You see that this quantity plays a critical role in determining whether the PSP is an IPSP or an EPSP. So E sin is the nonce potential of the synaptic channels, whereas V rest is the nonce potential of the, not nonce potential, the combined potential of all the other channels on the postsynaptic side. So it's an interesting term, and this difference plays a key role. Now, just to have an understanding of what will happen when I give a pulse current, because G sin acts like acts like a small pulse, right? So so this whole current acts like it's like a pulse current. So when you give such a pulse current, how does the voltage vary? What does the voltage deviation look like? So basically, the equation is of this form, roughly of this form: tau dx by dt is equal to minus x plus it, where it is like a pulse. Let's assume it's a pulse. Then, in response to that, xt will show an exponential rise as long as the pulse is there. After that, it shows exponential fall. Also, if the pulse is a positive pulse, then the xt response is also positive. If the pulse is negative, xt is also negative. And the time constant which governs the exponential rise or exponential fall is tau. So same thing here also. Right, so let's keep this in mind to understand this equation. So now we have three cases. One is when E sin is greater than V rest, when next E sin greater than V rest. Third is when E sin is more very interesting, when E sin is roughly equal to V rest, then what happens? So the first case of E sin greater than V rest, so this is like when the IT is a positive pulse. When this is true, right, your IT is positive. So you have a positive current pulse. So obviously in response to that, this small v also goes up and goes down. So this is obviously an EPSP. So the condition for EPSP is that E sin must be greater than V rest, right? So similarly, when you go to the second case, E sin is less than V rest. So then you can easily show by the same argument that the current is now negative. So negative current pulse. Therefore, the voltage deviation is also negative. So therefore, it is IPSP. So both are quite simple. Also, here I just want to point out that so our earlier understanding is that if you have an excitatory synapse, you'll have an EPSP, and inhibitory synapse, you have an IPSP. That was a kind of simplistic, understanding. Whereas a more precise mathematical understanding is given by these results, because here we have right. So the more precise condition is this quantity is in minus virus, is it positive or negative? So that's what determines your whether it's IPSP or EPSP, right? It doesn't depend only on esin, because esin will be positive generally if you're suppose it's a sodium channel, esin is a positive quantity. If it is a potassium channel, esin is a negative quantity. But the point is that alone doesn't determine the whether it's an EPSP or IPSP. It's the difference between esin and vrest. That's what determines whether it's esin or isin. So just we need to remember that. Because if esin is negative, even though it is negative, if it is not less than vrest, all right, then you won't have an IPSP. So this is a more precise condition that tells us under what conditions you have an EPSP or an IPSP. Okay, now let's take the third case, which is when esin is equal to vrest. So here this is an interesting case. So if you apply this to the same equation, then even though there is a brief increase in the synaptic conductance, since E sin is roughly equal to Vrest, there's hardly any current here. So there's no voltage response, which is interesting because there's a synaptic transmission, but there's no current. That's also possible when E sin is roughly. So E sin could be a kind of a, let's say potassium channel with a negative nonce potential. And let's say it so happens that that battery is of the same value as that of Vrest. The Vrest is a combination of many channels. Right, when that happens, then even though there's neurotransmission, there's no current. This is also possible. And some potassium channels, some chloride channels having GABA synapse with the GABA receptor, right, can have this kind of situation. So where even though there is transmission, there is no response. But then you might be wondering, like as an engineer, when you have something, you should serve some purpose, right? Whereas here you have something which doesn't serve any purpose because there's a synapse, but it cannot communicate anything. So what's the point in having such a synapse? Yes, when the synapse is used in isolation, it doesn't seem to have any effect. But when it is used in conjunction with an excitatory synapse, right, it seems to have an interesting role. Let's see what that is. So to understand that, let us add an excitatory synapse in addition to the this kind of a synapse where esin is equal to vrest. So let us call this kind of a synapse some kind of a zero synapse because it has zero effect when used in isolation. So we will call that synaptic conductance G0 sin and that nonce potential E0 sin. Okay, so it so happens that E0 is roughly the same as vrest. So therefore this term can be ignored. Now imagine a kind of a postsynaptic membrane where there is a presynaptic side. Let me imagine this. I'll draw a kind of weird. So here I have this kind of a. This is the zero sin, whereas this is my excitatory synapse. Right. So both having the inputs at the same postsynaptic terminal or postsynaptic site. Maybe you can move it around a little bit. Right. Then you can model this total current going to the postsynaptic side will have context. So let us assume that both of these inputs or axons fire at the same time. Let's assume that. Right, let's take that condition. So then what happens is there is a pulse current due to 0 sin, another pulse of current due to E sin, right? So if you combine this, so this term will go to 0, no effect. So this term is like the standard excitatory input. But the point is, if you look at, so since this is the 0 term is removed, you only have the excitatory term. Therefore, it will appear as if this equation is similar to uh, this equation, the excitatory case, right, where there's only CdV by dt and then the conductance times V term plus the input current, which is excitatory. But point is, if you look at it closely, there's one more term here, which is this term, and this becomes 0. But if you look at this term, the first term, you have, so even though the second term, the current term becomes 0, in the first term, you have sum of 3 conductances, G0, GE, and 1 by R. Had it been just an excitatory input or with an excitatory synapse, in this term, you will just have GE sin plus 1 by R. Whereas because of the presence of this 0 synapse, among these conductance terms, you will also have an extra term which is G0 sin. So this is not 0. So this whole thing is 0 or approximately equal to 0. But this is not 0. This is still there even though the corresponding current is not there. So because of that, what happens? You still have this additional term. Because of that, right? You can, for the same input current pulse, because of the additional term in the conductance, the voltage response will be lower. Okay, so for example, if I think of the GE sin as this current pulse, in response to that, I'll have a voltage response like this. So this is V of t. This is with without G0. Okay, and with G0, it will be a smaller amplitude. So what do we learn from this? Even though the 0 synapse doesn't contribute any current, its presence along with another standard, excitatory synapse, right, will act like effectively like some kind of inhibition and suppress the amplitude of the voltage response. So it suppresses the PSP that is produced by the excitatory synapse. So the PSP that is produced by the excitatory synapse acting in isolation will be higher than the PSP produced by the same synapse when it is acting alongside the 0 synapse. So this acts like some kind of inhibition, and that kind of inhibition is called shunting inhibition, because it's drawing away some current, some out, right? It will effectively inhibit the voltage response. So that kind of inhibition is it's like a silent inhibition. All right, it's called shunting inhibition. Okay, so that is it's a simple model of neurotransmission. We have seen what kind of events pan out on the postsynaptic side due to the neurotransmission. So with that, let us wind up our discussion of